So in this video, we're going to do step C of our fire station example. Part C says, use the greedy heuristic to determine a solution to the set covering problem. So in the previous video, we found the optimal solutions. We used the Excel solver to find the optimal solution. We're now going to use a greedy heuristic to find a solution, which is usually a pretty good solution. It's always guaranteed to be feasible, but not guaranteed to be optimal. And so as a reminder, I've just pasted the 4 steps, which are found in the slides, of this greedy heuristic. So step 1 says if Cj is 0 for any of them. So this is our Cj, none of them are 0. So you can kind of ignore step 1 for this problem. And so then it says if Cj is greater than 0 for any of these, and there's no +1 coefficient in any of the remaining constraints set xj to 0. So here we have all our decision variables set to 0 because that's what we're going to figure out. We're not going to let Excel solver figure that out. We're going to use the heuristic to figure that part out. And these are just the Aij matrix we did in the formulation and also used in the optimization part. And so just as a setup here, I'm still doing the sum product of our decision variables times this coefficient Aij. And all of those have to be greater than 1. And so if you look here, all of the 11 decision variables, there's at least one coefficient that's 1 for all of them. So we can skip step 2. So then for step 3, it says for all the remaining variables, in this step that would be all 11 of them, we need to determine Cj divided by Dj, where Dj is the number of covering constraints in which xj appears with a +1 coefficient. So what we need to do is we need to figure out Dj. That is the sum of our Aij variables. So if we click here, that's the sum. So for D1, that's 4. And for D2, that's 4, 6, and so forth. So I'm just summing up, again, the coefficients that are there. So that's Dj. And then it says in this step, we need to determine Cj divided by Dj, right? So we would say Cj divided by Dj. And as a reminder, Cj is just our coefficient in our objective function. So that's here. And then Dj, we just calculated, right? So that's there. So for this one, that's 10. And we can just move that across, right? So that's our calculation for all of these. And then in step 3, it says we should select the variable, the decision variable, for which this ratio is the minimum. So if we do that, we can say minimum. So I'm just going to say equals min. What is our minimum value here? Right? Our minimum value is 3.33. That occurs here, right? So that occurs there. I'm just going to highlight that. So that means we should set x3 equals 1. Why? Because this one's associated with x3, right? All right, so we set x3 equals to 1. So that's what step 3 says. And then it says remove all constraints in which here our k is 3 for this one. That's the one that was the minimum. So x3 appears with a +1 coefficient and examine the resulting model. All right, so in other words, everything that has a +1 here, all of these constraints, if we set this one to 1, what happens is these constraints here are feasible. So because I built in location 3, neighborhood 1 is good, neighborhood 2 is good, neighborhood 3 is good, neighborhood 4 is good, 5 and 6, which you can examine over here mathematically is all of those constraints are feasible. So what it says is we can get rid of those constraints. We still need to make more decisions of where to build because we don't have all of them finished. But it doesn't matter about these. If we also build in, let's say 1, okay, great, 2 is still greater than 1, it's still feasible. But we can ignore them in the sense that they're already feasible, okay? So what does this say? It basically says eliminate all of the constraints that are feasible. And so that's what I'm gonna do. So I'm just gonna copy and paste here the decision variables and our objective function. Paste that here. And then I'm going to only paste the constraints that don't have that are not feasible. So that's only these ones here. So I'm going to paste those there. And then we need to make sure I need to do the sum product because I had it up here. I want to make sure that this part is the new decision variable. So it's going to be this one. And I'm going to $sign that. And you can, and then I'm going to drag it down. Okay. And you notice all of these are 0 because we only are building in neighborhood 3. And just to kind of help so we can see which neighborhoods these are, I'm just going to add a thing here just so that we can better see that. Okay. So now it says examine the resulting model, and it says if there are no more covering constraints. Well, that's not our case. We still have these covering constraints. And so it says then go to step 1. And we can kind of skip step 1. They all have xj or cj's equal to 0 for this problem. And it says if there's no xj's that appear. So we're in step 2. So you could think about these ones here are explicitly set. We would explicitly set this to 0. This one to 0 because there are no x's here, and this one to 1. Okay, so these ones are we can say are kind of off limits. So I'm going to unhighlight them and say we don't have any control over them. So we've marked them and set them. So that's what step 2 says. And then step 3 says we need to do this CJ divided by DJ thing. Okay, so we need to again calculate these things. Okay. All right, so we start here because 1, 2, and 3 have been fit. So we just again sum up our coefficients here, and we do that for all the remaining ones, right? And then CJ again is still just our coefficient. Which again is here, and we need to divide that by DJ. And we can then roll this over. And as you can see here, we have different values because while the CJ doesn't change, the DJ does, but we need to now again get the minimum. So equals minimum of all of these, right? And the minimum here is 5, okay? And so this is the minimum, so I'm gonna highlight that, 5. And so what does this say? This says we should set x10 equals to 1, okay? So that's where I'm gonna move this one here to 1. And I'm going to highlight that I just did that. Okay, so now that I move this one to 1, what happens is all these constraints here are good. Right? So these are all satisfied. And so we can then get rid of those constraints because they're satisfied. So the only ones that are left is we have neighborhood 7 is the only one that is not feasible. So that's the only one we're going to bring with us. And so I'm just going to again copy and paste this down for the next step. And then the key here is I got to update so that it's the right decision variables, which is this set here. And then use the $sign. And you see here that we have, again, that this is not right. But now we can see, okay, this one here, there's no coefficient, so we will permanently set that to 0. So that one is no longer in play. Also 9 has no coefficients left, so that one is no longer in play. And 11 has no coefficient variables left, and so we'll set also that one to 0. All right, so, and this one is set, it's fixed, so it's out of play as well, okay? So we have one last neighborhood to do, and so we can do, again, this aspect. The DJs here are just the sum of this single one. So they're what's here. And so for the ones that are still in play. And then CJ again is given as the coefficient up here. And then we are dividing it by our DJ. And we'll do that for the ones that are in play. And then again, we need the minimum. So equals the minimum of the ones in play. And so for this example, the minimum is 40. That means this guy here is where we build. And so we should build, that means we should set x7 x7 should be 1. And so if I do that, I set that to 1, you can see here that the last remaining constraint is satisfied. And so the next step would say delete this, and then there's no more set covering, and so we're done, okay? So what did we just do? We just solved the set covering problem, and we can go and plug it back in to see what happened. And so just as a reminder, we set, in the first stage, we set x3 to be 1. In the second set, we set x10 to be 1, and then we set x7 to be 1. Okay, so that's our decisions. That's the values of our decision variables. And so we can then figure out what does that mean in terms of our solution. So what we did here is we just set 3 is 1, 7 is 1, and 10 is 1. And so if I plug that into my objective function, which remember, objective function is the sum product of our decision variables times these coefficients, we get that this is 80,000. And so if you remember, that's the same as our optimal solution. So in this specific example, we have the feasible solution and an optimal solution. So that does not always happen. You are not guaranteed to get an optimal solution, but typically this heuristic works really well for most problems. And so it's actually very useful and is used in industry a lot because heuristics are faster computationally than getting an exact solution, and they usually do pretty well on most problems. And so for this example, again, we build in 3, 7, and 10, and that cost us an objective function value of 80,000